So far, our study of rotational dynamics has been focused on torque, rotation of rigid bodies, and rolling motion. So the second part of our study is going to be focused on angular momentum. Now, angular momentum is given the symbol capital L. It's a vector quantity. And we're going to break our study of angular momentum into two parts. Angular momentum of a point mass, and then we'll give emphasis to angular momentum of rigid bodies. So this lesson is all about the angular momentum of a point mass. So let's start with a brief discussion about baseball. Let's say a batter steps up to the plate, and then the pitch is thrown, and the baseball is coming toward the batter. The baseball certainly has momentum because it has a mass and it has a velocity, and we know that momentum is just equal to the product of mass and velocity. But the ball also has angular momentum. Now, angular momentum for a point mass is defined as the cross product of a lever arm with linear momentum. So the units for angular momentum are, well, let's see. Regular momentum has units of kilogram meters per second, and then a lever arm has units of meters. So angular momentum has units of kilogram meter squared per second. So let's see, how do we define the lever arm in a case of a baseball being thrown toward the plate? So let's imagine two cases. Number one, a ball thrown as a strike. In other words, the ball goes right across the middle of the plate. So we'll say we have a reference point at the center of home plate. So let's draw in the momentum vector. P equals mv. So lever arm, in the same way that lever arm is defined in calculating torque, lever arm is the distance from the point of reference to the location of some other vector. So from the point of reference to the object that has momentum P equals mv, there's a lever arm of r. Okay, well, yeah, there's a lever arm, but there's no cross product, right? The angle between these two is 180 degrees. The lever arm points directly to the left, the momentum points directly to the right, and so the cross product between those, the angular momentum, is the cross product between the lever arm and the linear momentum. So in this case, our angular momentum is 0. Now let's consider another case where the pitcher throws a ball. So the baseball follows a line that's off the plate, but we still keep the center of home plate as our point of reference. So now we've got a momentum vector that points to the right, and we have a lever arm that points from the reference point to the object, and there's some angle between those two that's not equal to 0. So we can break that lever arm into two components. There's a component of the lever arm pointing to the left. We can call that R parallel, the component of lever arm parallel to the momentum. And then there's another component to the lever arm that points along the y-axis, and we can call that R perpendicular. So the angular momentum in magnitude, because it's a cross product, then in magnitude, it's equal to the momentum times the lever arm times the sine of the angle between the two. But I want you to notice, if we consider r sine theta as one quantity, well, the parallel component to the lever arm is r cosine theta, and the perpendicular component is r sine theta. So what we're really saying is the magnitude of the angular momentum is the magnitude of the linear momentum multiplied by the perpendicular component of the lever arm. Now notice, for the baseball, as it travels to the right, let's say the baseball reaches this position. Is its angular momentum greater than or less than it was prior? So we can look at the ball at point A and the ball at point B. Is the angular momentum greater at point B? Well, if we ignore air resistance, then the linear momentum is a vector that's still of the same length. The linear momentum is a vector yay long, and if air resistance is negligible, then by the time it reaches point B, it still has the same amount of linear momentum. Okay, so that part of the angular momentum hasn't changed. But the lever arm looks like it's become shorter. Yeah, we've got a shorter lever arm now. So it's probably less angular momentum, right? Well, no. It's not the linear momentum times the total lever arm, it's the linear momentum times the perpendicular component to the lever arm. So if I break this lever arm into components, it has a shorter parallel component, but it still has the exact same length perpendicular component. So what this tells us is the angular momentum at point A is identical to the angular momentum at point B. And it ought to be, right? Because there's not only no external force, remember we're ignoring air resistance, but there's no external torque. So we might say something like this. Newton's first law of motion, the law of inertia, says an object will maintain constant momentum, right? P is constant if the net external force on a system is equal to 0. That's equivalent to saying an object at rest stays at rest and an object in motion stays in motion in a straight line. Linear momentum remains constant when there's no external force. Well, in the same way, angular momentum is constant if there's no external torque. And there's no external torque acting on a baseball that flies through the air, so as it follows a straight line path, its angular momentum at point A, its angular momentum at point B, and even its angular momentum here at point C are all of the same value. And that value is mv r perpendicular.